Hello everyone, in this video we are going to build this rope solver or thread solver using the Verlet integration method as well as this XPBD method. And in this video I'm going to cover the topics like integrations, Euler integrations, Verlet integration and XPBD method. And these are really important concepts to build any kind of solver. So this is going to be a detailed tutorial. So let's get started. So we have this new file. Let's add an object. And this is going to be our thread solver object or rope solver object. And then we need the curve for the rope or for the thread. This is going to be initial curve. So you may notice why I have added a separate object for the solver instead of building the solver onto this curve. Because the geometry nodes works in the local space of the object. And if this curve has some kind of animation, then it will be difficult to extract that data for the solver. It is always better to make the solver or build the solver onto a separate object. So we have this. So let's add the geometry node. We can delete this. Let's bring the curve. Okay. And let's connect that to the output. So before we start, first I'm going to explain the integrations, why we need the integration like Euler, Verlet integration to build this solver. Okay, not this solver, but any kind of solver like a particle system, claw simulation, etc. Now suppose if we have a particle in the space like this, we have this particle, and to describe its motion in the future means where it will go, it may go something like this, something like that, or something like that. So the future trajectory of this particle can be calculated precisely using the two parameters. One is it is position, another is it is velocity. So with these two parameters we can calculate it is future trajectory. Okay, and suppose we have this second particle and there is force, and so the particle may go something like that, or may go in the reverse direction, or go something like that. So in this case we need a extra parameter, position, velocity and acceleration, or you can call this as position and total velocity. So what is total velocity? Velocity is the initial velocity of the particle and the velocity which is affected by this acceleration due to force, is some kind of external force. Okay, so if we have these situations, we have particle at its position and velocity. So you know that the velocity is the rate of change of position with respect to time. Okay, so this is the differential equation. Okay, by solving this we can calculate the position of the particle, but this is the differential equation, and this parameter in this differential equation is infinitesimally small, so we can't do that in computer. So instead of this we solve the difference equation, okay, in computer graphics. So this is the difference equation. So in this the delta x is basically like the next position, or called the final position minus the initial position, and this time is like final time minus the initial time. Or if this time is constant, this time step is constant, maybe in second, milliseconds, then we can also write this as delta t, which is the time step, or in our case the delta time. Okay, so from this we can calculate this delta x by bringing this delta t to this side. So we can write something like delta x is equal to velocity into delta t. Okay, or simply velocity into delta t. So we have this delta x, or the smallest increment in position based on this velocity in this time. Okay, so the final position will be xn plus 1. The next position is equal to current position plus this increment. Okay, delta x, or we can write something like delta t. Okay, so let me also add these things. So this is the x position, and it is past position going to be x minus 1, and it is future position going to be xn plus 1. Okay, So with this formula, we can calculate the position of the particle, okay, based on the velocity. So now we have this second situation where the particle experience some kind of external force. We need to include the effect of that force inside this velocity of the particle. So the acceleration is equal to the rate of change of velocity with respect to time. So similar to this, we can write this as acceleration is equal to delta v over delta t. And from this, we can calculate the delta v is equal to acceleration into delta t by bringing this to this side. So now we have the increment in the velocity based on this acceleration due to external force in this time. So from this, first we can calculate the velocity, new velocity, going to be the current velocity plus this increment, or we can write this something like a into delta t. So we have this new velocity. So based on this new velocity, we're going to calculate the new position or the delta x. So delta x is equal to Vn plus 1 into delta t, or we can write this here. So this is going to be Vn plus a into delta t multiplied by delta t, or we can write Vn into delta t plus a into delta t square. So we have this, and from this we can calculate the new position. The future position is going to be xn plus delta x here. So we can put this value, which is going to be Vn delta t plus an a delta t square. So now you can see that this is similar to the previous case, see, but it has this extra part, okay. This extra part is due to the external force, and you can see that this force is affecting the position as well as it is affecting the velocity, okay. So from this we can calculate the position of the particles in the future based on this formula when there is some kind of force is present. So this is also known as Taylor expansion or simple Euler integration, okay. So then we have the Verlet integration. So now you may ask why we have this Euler integration, Verlet integration and other methods. Because we can't solve this differential equation, we are solving the difference equation, and this difference equations introduce some kind of error to the solutions, and different methods provide different order of accuracy in different situations. Like I built this particle system based on this Euler integrations and it works well. And there are other methods like RK methods provide a more accurate solution to this to the particles physics. So to build the rope solver, we need to satisfy some constraints like distance constraints, collision constraints, so that are easily doable with the Verlet integration. Okay, I'll provide some of the video links in the descriptions. From there you can watch the in-depth explanation of this Verlet integration and why it is better than the Euler. Okay, so this is the Verlet integration. So in the Verlet integration, xn plus 1 is given by 2xn minus x minus 1 plus a into delta t square. So we have the current position and we have the previous position, and then we have the part from the force. So you may notice that there is no velocity. So in this case, the velocity is calculated from the previous position. So that I'll show you. So we have xn, we can break this into xn minus 1 plus an into delta t square. So we can divide this by delta t and multiply it by delta t. So this is velocity, you can see from this. Okay, so this is the velocity from the previous position. So we can write this as xn plus vn minus 1, this one, then we have this delta t, and then we have this delta t square. So we're going to use this form for the rope solver instead of this, because this is much clear and easy to understand. So now you can see that it is comparable with the Euler method, but in this case the velocity is from the previous position. Okay, And there is another better alternate to this Verlet integration, that is XPBD method. PBD means position based dynamics. Okay, so this is PBD. So this is XPBD. I'll talk about later in this video. I hope this clears some of your doubts. If you have any other doubt, please let me in the comment section. Now let's build the rope solver based on this formula. So in this formula, we can see that we need to store the previous velocity as well as the previous position. Okay, so let's bring this to here. So let's first resample this curve based on the length, and then we need to add the store node like this. Change this to vector. So this is going to be our previous velocity, and this is going to be the previous position. Because our previous velocity at the start is 0, so we can use the current position as the previous position. However, if there is some kind of previous velocity, so you can backward calculate the previous position. Okay. Now let's add the simulation node. So first we're going to build this term, velocity, previous velocity into delta t. So before that, we're going to store our previous position, because in the next step, we're going to use this as previous position to calculate the velocity. Then we're going to add the set position node. Okay. So let's add the named attribute node, previous velocity. Then we're going to add the vector scale node, and we're going to multiply it by this delta t, which is delta time. You can also use the custom time. So we have this term. Then we need to build this, which is acceleration into delta t square. So let's duplicate this one. I'm going to make this -1 to mimic the gravity. Then we need to multiply it by delta t square. So we have this delta t square, then multiplied by this. Then we need to add them together like so. Now we have these two terms. So you can either use this as offset, or if you want to add this term, you can use this as a position, okay, not as offset. So let's move this to here, like that, into this. So now we have completed this formula. So this is our xn, and this is our velocity into time. This is acceleration into delta t square. So we have this complete setup. So now we have updated the position. So now we need to calculate the velocity using this previous position. So let's duplicate this node so that we can store the velocity. So let's first add the position. This is the current position. Then add the subtract node. Then add the named attribute node to get the previous position, which is pre-position. Then we need to divide this by a time. So you can see that here. Okay. So let's duplicate this one. Change this to divide. And we're going to divide this by this delta t or delta time. So we have this velocity. We are updating the position. Here we are storing the previous position. Let's see. See, this curve is falling under gravity. Nice. Now we need to implement the constraints for this thread solver or for the rope solver. The first constraint is we don't want to move these ends. Okay. So let's add the end selection node. So let me show you this. See, these ends are white or have true value. We don't want to move them. So let's add the not. Convert of that. Use this for the selection. for this selection and for this selection. So we don't want to update it is pre-position, it is current position, as well as it is velocity of the endpoints. See, they are fixed here. Now we need to add the distance constraint. You can see that this stretch, so we have to build up the distance constraint. So to build that, we're going to use the radius of the curve points. So let's first set the radius of the curve points. I'm going to set this as half of this length step, and in the outside we're going to instance some icosphere so that you can better understand what is going on. Let's add the icosphere, use radius, and also use 3. So if you refresh this, you have this, and also let's combine this curve. Okay, now you can see that they are perfectly packed together. So in the ideal condition, they should remain like in this straight line. Okay, so we will try to match this ideal condition with our constraint. So let's add a reroute, press Ctrl G to make a group, rename this as geometry. So the constraint is when these points are far away, like in this case, so their distance is larger than their radii sum. Okay, this radius sum. So when this is the scenario, we have to move these points toward each other. Okay, so that they satisfy the condition, which is their separation distance should be equal to the radii sum. So let me show you this. So this is going to be the ideal condition, something like that. Okay, so this is the separation distance d, which is equal to r plus r, the radii sum. Okay, so if we have this case, something like this, so their separation distance is larger than their radii sum. So in that case, we need to move this point to this side and move this point to this side so that they match this condition. Okay, means their separation distance is almost equal to their radii sum. Okay, you may ask, there will be another case where these points are overlapping, something like this. In this case, d is going to be less than their radii sum. So for this, we're going to build the collision constraint. Okay, so this is our distance constraint. Okay, this is our collision constraint. So let's build this. So first we need to add the set position node, and then we're going to bring that selection, this endpoint selection, because we don't want to move the endpoints based on this constraint. And then we need the offset point in curve node. So first we're going to check for the previous point. So for that we need to add the switch node, because the endpoints don't have their previous point or the next point. So we need to add here index. So what it will do, let me show you this. It's going to output the same index when it is at the end of this curve or the end point. Okay, and same thing we're going to do for the next point. So for the previous point, we need it is position. So we're going to use the evaluate index node. We need it is position, and also we need it is a radius. Then add the radius. Okay, next we're going to subtract this position from the current position. So this will give us the vector, this vector as well as the distance. So we can normalize this. So this is the vector in which direction we want to move the point, and from this we can calculate the separation distance. So if this separation distance is larger than their radii sum, so let's add these radius, current radius and this previous point radius. So we have this condition, and let me show you the numbers. See, it is almost 0 here because these points are at same distance at their radius sum, but it is larger here if we compare this. See, and another condition is it should be maximum by 0 because we are only doing this condition, not this condition. So when this is negative, we have to do this collision constraint. Okay, so we have this. So now we need to move the current point by this offset, and let's add this offset to the current position. So let me show you this. If I plug this into this, see it move the current point to this location. So let me disable this. So here we are only checking for the previous points. Okay, so this point have this previous point, and the another point, this point have this previous point, this point have this previous point. But we need to also check for the next point. Means this point have this next point, this point have this next point. So let's duplicate that, make this +1. This. Now we are at the next point. So if I use this, see, nothing happen. If I just off this selection, see, it is moved the end point to this side. Okay, we have two corrections for the previous point and for the next point. We need to correct the current point for both the correction. So we can do that by just adding them together and then dividing by 2. So basically we are taking the average of both the correction. See, it is centered between these 2 points. So now we are done with this distance constraint. So let's go outside, rename this as KS distance constraint. Okay, so let's see this. See, it try to preserve the length, but had failed at some point because we are only correcting this once. If we add this twice, it's going to make it stable. See, and to make it more accurate, we have to add many of these. So for that, we can use the repeat zone node. Let's add this to this and this to this. We can delete this and add this constraint inside this zone, repeat zone node. So with these iterations, we can add many number of constraint steps, type 10, or let's type maybe 100. Okay, so with the 100 iterations is much better, but still we have a small error here. So that going to fixed with this XPBD method. Okay, so now let's build the collision constraint. Okay, so that is going to be our these situations when these points are overlapping with its nearest point. So we're going to move them apart. Okay, so let's go to the top view, first frame. Let's duplicate this curve, something like here, and let me also decrease the number of iterations because I'm recording. So let's use 50. See, these points are overlapping, so we have to correct that. So let's add a reroute, then press Ctrl G to make a group. So let me change this to geometry, and first we need the set position node, add the selection, and then we need to connect this to this. So this is our case. collision constraint. Okay, now we need to provide the offset for this overlapping. So we're going to use the index of nearest node. So based on that, we need the position and radius of the nearest point. Position, duplicate this one, then we need the radius. So first we need to calculate that separation distance using this technique. So this is the separation distance, and if we normalize this, we get the vector in which direction we need to offset the current point so that it satisfies the distance or the collision constraint. So if the separation distance is less than their radius sum, okay, so this is the radius, and then we need to subtract this from the separation distance. So let me show you this. See, these negative signs means the points are overlapping. So we need to add the minimum by 0. So these points are overlapping, which are non-zero. So we need to move the current point by half of this offset because we are dealing with 2 points. Okay. So let's add the vector scale node, and then we need to divide this by 2 because we are checking for 2 points, and then we need to offset the current point by this offset. So let's go to the first frame, close this and see this. See, they are not overlapping. And to make this constraint better, we can move this constraint inside this repeat zone node. Okay, so let's move that here. So both the constraints are inside this, and let's see. Nice. So this is the rope solver based on the Verlet integration method. So now let's build the rope solver based on XPBD method. So let's duplicate this one, rename this, okay, and also connect this to the output. Actually, when I was building the rope solver based on this Verlet integration, I have noticed that if I add a substep to this method, it makes the simulation stable and more accurate. So that substep method I previously used in my procedural particle system. So that is precisely the XPBD method. Okay. In this Verlet integration, we are doing basically, we have this time step, which is delta t. And in this step, we are doing 50 or higher number of iterations of constraints. Okay. So we are doing this number of constraints in this one time step or one frame step. So in this method, we're going to break this delta t into substeps, something like that. Let's call this delta I. So in each substep, we're going to solve this distance constraint instead of solving by this number of iterations. Okay, we're going to solve this based on this number of substeps. So that's going to make it much more accurate and stable. So for this, let's first delete the repeat zone node. Let's move this to this side, and also move these nodes to this side, something like that. So we have this time step. Let's bring that here. Let me also make that readout here so that it will be easy for you to compare both the methods. Okay. So in this, I'm going to first add the divide node, plug that here, and here we're going to use the number of sub-steps. So let's add the integer node. So this is our sub-steps. So let's use 10, and we have this 10 sub-steps. Then we need to do this whole dynamics in each sub-step. So for that, we're going to add the repeat zone node, but we're going to use that here instead of for this distance and collision constraint. And this iteration is going to be the number of sub-steps. So now probably you can see that. So this is the sub-step dynamics. Okay. And this is the frame dynamic, or the one-time step dynamic. So now let's rerun this. See, it is stable. It has more accurate motion, as well as satisfying this constraint only with 10 sub-steps instead of this 50 or 100 iterations. And we can compare them side by side. Let's duplicate this one. So use this as the curve for this, and let me duplicate this one, add these together. So we have this, and let me also go to the first frame, and this is the Verlet integration. So this is the Verlet integration. So this is the XPBD, or the sub-steps. Okay. So now let's see this. Let me do this for 100 frames. So this is the final frame. See, it is using 50 iterations and it is using only 10 iteration. Okay. And another thing, you can also convert this into rope. Just duplicate this one, combine them, then convert them into mesh, and use here curve circle. Now you have the ropes, and let's also fill the gaps. So now you have the ropes. Okay. And another thing you can do that is, let's animate the fixed points. So initially they have the fixed point, and after 40 frames we're going to make this 0. They detached from their fixed points. And let me show you the open-end simulation. You can see that how end snaps really nicely in XPBD methods. See, this is it. I have posted the extended version of this video on my Patreon page, where I have shown that how to pin the endpoints of this rope and the collision with the external objects. And you can also get the project files and other my assets from my Patreon page. So I hope you learned something from this video. So if you like, then please like and share the video and subscribe to my channel for more updates. See you in the next video. Happy noding. Bye.